So, hello everyone again. This is lecture 2 part 1 of wave optics. In the last lecture we were studying about the Huygens principle. In the lecture 1 also we also started with the chapters introduction. Why is there necessity of wave optics to come into picture? Why was only ray optics or the Descartes theory was not only allowed or was not only sufficient for the propagation or the wave model to come into picture, why only the ray model was not sufficient. We learned about that chapter. Today we will start with some of the shortcomings of Huygens principle and take the discussion further. So, I am Samir Lavankar. Let us begin our discussion. So, first of all, a little course outline for you. So, in the last lecture we started with the introduction of this chapter. Today we will go in much deeper discussion of Huygens principle only. After the Huygens principle we will study about the refraction and the reflection of plane waves using Huygens principle. So, how is the Huygens principle being applicable to applying the laws of reflection and refraction. After this we will study a new concept called as coherent and incoherent addition of waves. A little detailed discussion is required for number 4, and then further we will go on with the further discussions. So, just a quick recap of the Huygens principle. Let us say I drop a small stone into a calm pool of water, then these complete ripples which form, every of these circular rings have a what we can say is constant displacement in the upward direction. So, the constant the locus of all these displacements which are at the same point from the source is called as a wave front. So, let us suppose that this is the first circle being shown here, this is the second circle being shown here. So, this can be the wave front at t is equal to t1 and this can be the wave front at t is equal to t2. So, such to iterate to you, such a locus of points which oscillates in phase is called as a wave front. Moving on. So, next thing we studied was ki every of these wave fronts is in a spherical form, and from the point of source each of the point of the spherical is at a equal distance. If the radius of the sphere is very large, let us say it is around let us say 100 meters or 1 kilometers or so, then a small part of that sphere can act as a plane, and the waves passing through can be considered as a plane wave. So, that concept is written here. So, at a large distance from the source, a small portion of the sphere can be considered as a plane, and we have what is known as a plane wave. So, this is a typical example of a plane wave passing through a plane. These can be considered as wave fronts at different time. So, moving on. So, one of the principles application was how, like, if we have a wavefront at t is equal to 0 and if you want to find out the wavefront at some t is equal to tau, then how will we calculate. So, we discussed in the last lecture only. So, let us suppose that this is the primary disturbance point. So, let me write it here for more clarity. So, let O be the primary disturbance source. So, now let us say at some t is equal to 0 we have this wavefront. The wavefront can be denoted as what we can say f1 f2. So, this is the wavefront being given to you. So, f1 f2 is the wavefront, f1 is written here, f2 is written here. So, what does Huygens principle say that each of the, let me iterate to you for more clarity and no errors. So, now according to Huygens principle, each point of the wavefront, so these are the complete points. Let us take any of the 3 points. So, the 3 points taken here are this point and this point. So, according to the Huygens principle, each point of the wavefront is the source of a secondary disturbance. So, as we know that O was the primary disturbance point, here let me denote these points as, let us say, D, E, F, then D, E, F are secondary disturbance source. So, DE a secondary disturbance source. There can be many infinite number of secondary disturbance sources depending on the points we took on the complete arc. So, here it is a complete arc only. If I complete it to circle, it can be a complete circle, but actually it is a sphere. So, any point on that sphere can be any point on that sphere which is at a radius of let us say I denote this by r. So, the distance r can be denoted as a secondary point disturbance source. So, what does this say? Let me iterate again. So, now according to the Huygens principle, each point of the wavefront is the source of a secondary disturbance. From the second disturbance source only there can be a small secondary wavelet being formed, and the wavelets emanating from these points spread out in all directions with the speed of the wave. So, as you can see, this blue color are nothing but secondary disturbances. These wavelets emanating from the wavefront are usually referred to as secondary wavelets. So, these are nothing but secondary wavelets. So, just to iterate to you again, let me write it here. So, the black color lines are the primary wavelets, and the blue color lines are the secondary wavelets. So, as the name suggests, the wavelets formed from primary disturbance source is known as a primary wavelet, denoted by black color here, and the secondary wave is being formed by secondary disturbance sources denoted by blue here. So, this is secondary wavelets. So, these, just to iterate again, these wavelets emanating from the wavefront are usually referred to as secondary wavelets, and if we draw a common tangent to all these spheres. So, now a common tangent is being drawn. So, as you can see why it is curved here, because if I let us say I point it here and I draw it here, I point it here, I draw it here, then a complete tangent will also be in the form of an arc. That is why it is not a straight line. So, if you draw a common tangent to all these spheres, you obtain the new position of the wavefront at a later time. So, at a later time as in if we need to find out at some tau. So, it is quite evident that the value of this radius will be is equal to distance is speed into time, speed is given to you as v, and time is given to you as tau. So, radius of this will be nothing but v into tau. Let us move on to the further discussion. So, the point I just said is written in these positions. Now, let us move on to today's discussion now. So, what was the shortcoming? So, let us please look over here carefully now from the third point here. So, the above model has one shortcoming. We also have a back wave which is shown as D1 D2. So, as I already iterated in the last lecture also, the complete sphere will be formed from these secondary sources. So, if a complete sphere will be formed, then the forward phrases are okay, forward points are okay, but what about the backward points? There are also, as a sphere is complete, the sphere will have some of the points which are situated backwards towards the wavefront, which is towards the primary source. So, what about this wavefront form? What about this D1 D2 wavefront form? So, now, so this was one of the let us say this was some of the things which is not accepted, because the wavefront cannot move backwards, it is moving upwards only, as in forward only. So, what was Huygens' argument regarding this? So, we also have a back wave which is shown as D1 D2. Huygens argued that the amplitude of the secondary wavelets is maximum in the forward direction and 0 in the backward direction. So, just to prove his theory right, he made some vague discussions, he made some vague assumptions, as in that the wavelet which is going forward will be having the maximum amplitude, and everything which is going backward which will be having 0 amplitude. But quite just think about it, if the concepts are being formulated like this, how can it be possible that something going forward is positive or completely and something going backward is 0, if taking the case that the resistance is 0. So, that so when the further discussions were being formed, it was found out that this assumption is vague, this assumption is ad hoc. So, Huygens argued that the amplitude of the secondary wavelet is maximum in the forward direction and 0 in the backward direction by making this ad hoc assumption as in any assumption made just to prove your principle or theory, and so that someone cannot falsify it. So, Huygens could explain the absence of the back wave just to make this ad hoc assumption. Ad hoc is, as I already told you, that it is just a vague assumption. Huygens could explain the absence of the back wave. So, how he explained this is written here, but actually it is not possible, as the wavefront only moves forward and onwards. However, this ad hoc assumption is not satisfactory, as I already told, it was an ad hoc assumption. So, this ad hoc assumption is not satisfactory, and the absence of the back wave is really justified from a more vigorous wave theory. So, when more general research was being done, it was found that a back wave cannot be formed, but the discussion or the proof of this was not related to Huygens principle, some more rigorous wave theory. If it comes, I will explain to you, but for now it is not required. So, is really justified from a more vigorous wave theory. In a similar manner, we can use Huygens principle to determine the shape of the wave front for a plane wave propagating through a medium. So, this last line is being explained here, please look out to this below figure. So, let us suppose, as similar to this F1 F2 being formed in an arc, let us suppose this F1 F2 is a straight line. So, this is F1 given to you, this is F2 given to you. So, let us suppose as this F1 F2 straight line, as it is a straight line, it is a plane. Anything which is passing through a plane is known as a plane wave. So, a plane wave is passing through perpendicular to the direction of the plane. So, let us say this is the plane, let me use this. So, let us suppose this is the plane and anything passing through it is known as a plane wave. So, this is the plane and this is the plane wave passing through like this. So, it is quite evident it is perpendicular to the direction of perpendicular to the area or parallel to the area vector. So, now let us say this is the wave front being formed at t is equal to 0 and we need to find out the wave front at t is equal to tau. So, quite easy. So, we will take any of the points at the wave front at t is equal to 0 and using a sphere of radius is equal to v into tau. As I already told you, distance is equal to speed into time, we will find out, we will make different spheres and directly after making this sphere we will draw a common tangent to all this and then we can directly find out the value of wave front at some t is equal to tau. So, this was the complete line explanation of the last line here. So, in a similar manner we can use Huygens principle to determine the shape of the wave front. So, this is the again shape of the wave front, quite evident that the shape of the wave front is again a plane. So, plane shape of the wave front for a plane wave propagating through a medium. So, this was a complete explanation or example of a Huygens principle being applied to find out the wave front at some tau t is equal to tau, given that you know the wave front at t is equal to 0. So, a little bit about Christian Huygens, he was one of the prominent scientists who made the Huygens principle. So, he was a Dutch physicist, astronomer, mathematician and the founder of wave theory of light. So, he is known as the founder of wave theory of light. Not very not important for your syllabus point of view, just to know a little bit about our scientists, that is why I added this here. So, he brilliantly explained the double refraction shown by the mineral calcite in his work in addition to reflection and refraction. So, apart from his laws or explanation of refraction and reflection from Huygens principle, he also worked on double refraction as in refraction being done twice, let us say in two mediums or so. So, he was the first to analyze circular and simple harmonic motion. I guess simple harmonic motion is being taught to you in some other chapter, and designed and built improved clocks and telescopes. So, using the time theory and all, he improved clocks and telescopes at that time 1629 to 1695. Guess today is 2023 going on, it is around 300 years back or 400 years back. And next he discovered the true geometry of Saturn's ring. So, Saturn's ring, so complete analysis was done, complete equations were being formed, and finally Huygens was the first one who discovered the true geometry of Saturn's rings. So, let us move on. So, now after the completion of the Huygens principle, we will look out to the how the laws of refraction and reflection can be proved using proved for the wave theory of light or the wave propagation of light using Huygens principle. So, refraction and reflection of plane waves using Huygens principle. First of all, we will go through the refraction of the plane wave. So, just to iterate to you everything, I will go very slowly. First of all, let us look at this diagram. Let me explain you whatever is required first and then I will add on. So, first of all, as you can see that there is an interface being formed here. So, I will keep on writing also so as to make everything clear. So, here P dash is nothing but the interface. Very interesting concept, just listen carefully. So, now P dash is the interface given to you. So, above is medium 1, above the interface is medium 1, above the interface is medium 1, below the interface is medium 2, below the interface is medium 2. So, from the wave theory of light, when we started the concept of when we started the introduction of the wave optics, we got to know that the Descartes theory said that when on an interface, when the refraction is being done and the light the ray of light bends towards the normal, then the velocity in the second medium is greater than the velocity in the first medium. But it was proved wrong when the experimental analysis was being done, and when the wave theory of light, or according to the wave theory, when Christian Huygens and other scientists worked on this part, when the refraction portion was being done, it was found that on the refraction, if the light bends towards the normal, then the velocity in the second medium is less than the first medium, and which was also being proved right by experimental analysis by Foucault and so. So similarly, it is written here that V2 is less than V1. Now let us suppose that this is ray of the light. Also this is also a ray of the light. So because of this complete ray of light and a wavefront is being formed, let that wavefront be denoted as AB. So let AB be the incident wavefront. Let me write that also here. So this time the complete light is not a single ray, it is a complete wavefront. So wavefront is being incident on the, what we can say, incident on the medium, or the, sorry, not on the medium, on the interface. So AB is the incident wavefront. So AB is the incident wavefront, and just to iterate to you, I will explain how this came, but for now let us suppose that this EC is the refracted wavefront. EC is the refracted wave front. So just to iterate to you everything again, this was the interface given to you as PP dash, this was medium 1, this was medium 2. On refraction, according to the wave theory of light, the velocity in the second medium is less than the velocity in the first medium. So complete this time, as it is not ray optics, this is wave optics. So a wavefront will incident on the interface. So this wavefront is incident wavefront, and after refraction the wavefront which will be formed is this refracted wavefront. Further discussion will be analyzed in the next part of this lecture only. For now I will stop it here only. In next lecture we will first understand what is the complete concept being talked here, why is there a tilt here, why is there a difference in the angle of inclination, what is the equations, what are the values of V1 tau, V2 tau, why is V2 tau less, and so on. So for now let me stop it here only. Thank you.